So let's start with a little story about myself. When I studied mathematics and computer science at the University of Duisburg-Essen, I took a master course called Numerical Analysis. One of the learning goals of this course was that students should be able to express mathematical problems in a given programming language, in this case MATLAB. Therefore I was very hyped for the course because it combined two things I really love: thinking about mathematical programs and programming the computer to do my work. Unfortunately, right around the first few exercises my hype got really dampened. Here's why. I was a computer science student who had already learned programming in Java. And therefore the exercises and tasks we got were quite frankly not too challenging for myself. So my initial enthusiasm to learn more about programming and programming in a mathematical way went away very quickly. But I also observed the other extreme. Some students who never programmed in their life struggled really hard with translating a mathematical program to MATLAB, because I think they needed to learn the mathematical concepts and the programming concepts at the same time. I think that these problems occur because lecturers do not know what previous knowledge their students have, and therefore they are designing courses and exercises material for an average student based on their previous experience. So if you think about yourself, you maybe also have encountered this problem in courses you have given or in courses you took. I, for myself, am now holding a course where programming is an integral part, and I'm dealing with the same issue. So I'm asking you to think about the problem of previous knowledge for a little while and how you would tackle it. So here's my approach. I think that not all students should receive the same material, and not all students should have the same progression throughout the course. I think that we need to adapt our teaching to each individual student. A necessary prerequisite for this is to gain information about which competencies students in the field of programming already have when they are entering the course. Therefore, we need valid and reliable assessment instruments which lecturer could use. And I know many of you have already produced great programming exercises. But if we think a little about it, we find two open questions. First, how can I as a lecturer find these assessments? And second, how can I as a lecturer pick the right one for my course? So to answer this question, we need to speak the same language, meaning we need to think about programming in a compatible way. We need to map terminology, which might be different across programming language, paradigms and use cases, to a common understanding. And therefore we need a model of programming which respects different approaches. So we did an analysis of books about programming languages, programming paradigms, and programming concepts in different contexts. For example, we analyzed Sebastian's book Concepts for Programming Languages and Computing for Biologists by Libeskind, Harders and Bush. Just two examples. We have included many more in our analysis. And this analysis led to a model of programming. So for us, programming consists of knowledge dimension and cognitive dimensions. And in our model, there are three knowledge dimensions: the high-level paradigm, elements, and the language. I will not go into detail about the model here, but you can find more information about it in our WIPC 2020 paper. There should also be a video on my YouTube channel which you can watch. Okay, let's step back for a moment. Now we have a generic model for programming which we can apply in different contexts. So we start looking at assessments which you have already published and see how these assessments align with our model and how they fit into it. Why do we need to do that? Why do I need to check how your assessments, which you might have a different kind of model in your mind, how does they fit in our model? So let's go back to the numerical analysis course, which I described at the beginning. Imagine that the lecturer would have based her or his course on our model. Let's not go into detail, but let's use this schematic. which shows the parts of the model which are relevant to the course. So now the lecturer wants to assess the previous knowledge of students. Of course, he or she could build a new assessment. But then there are other questions. Is the new assessment reliable? Is it valid? These are tough questions when it comes to assessment design, and they need empirical studies. Therefore, I think we should use what is already out there and what is already battle-proof. So imagine the lecturer would go to our database, she or he would put the parts of the model she or he cares about, and our database would provide a suitable assessment. This is our long-term goal. So to get this going, we have done a systematic literature review to find your assessments, which are already published in the ACM Digital Library. We then tag these assessments with parts of our model. We also investigated if the researchers took care of the validity and reliability of the assessment. How did we do that? So we defined a search query for the ACM Digital Library and checked the first 500 relevant entries. From this 500 relevant entries, we took 470 papers where we could also access a PDF. And from this 470 papers, we found 23 papers which introduced a new assessment. And this was our eligibility criterion. That's a paper needed to propose or to introduce a new assessment. And some of those papers also introduced more than one assessment, so we, after all, found 26 assessments. Unfortunately for us, only 13 out of the 26 assessments were publicly available, meaning the assessment was either in the appendix of the paper, integrated in the paper, or a link to the assessment was presented in the paper. And this is crucial for us because tagging an assessment with parts of our model is relying on seeing the items. So we only included these 13 assessments in our deeper analysis. But before we start with this deep analysis, let me show you what assessment we have found, so the 26, and which content areas the authors claim the assessments cover. So here you can see they are covering a wide range of content areas. As you can see by looking at the number of items, we found assessment which only contains a smaller number of items, like 5 for example, and assessment which contained a huge number of items, for example 40. So what is also interesting is that we mostly found assessments which were published after 2012. But maybe this is the first limitation of our search. Maybe the ACM Digital Library handles older paper in another way than newer paper when you sort the papers by the relevance. So, okay, this is the overall picture of the 26 paper. Now let's dive into the 13 assessments we could access. In terms of programming languages, the majority is using Java or some kind of pseudo language. When we cluster the assessments by a high-level paradigm, we see that the imperative one is the most common, followed by the object-oriented and the procedural. So now we take care of the elements dimension, which is language and paradigm independent, so it's of great value for us. So let's work through the different parts of this elements dimension. So in the area of programming components, we see that the assessments, all assessments handle assignment and variables. Some of them also include method calls, some arithmetic operators, few less, the if statements, rational operators, follows, and so on. And they also handled different data types. Some of them handled different basic data structures like lists, queues, and stacks. And most of them were implemented in an iterative way. So the code questions are most likely about iterative programming, and only one assessment also asked about recursion. So here you can see the overall coverage of the assessment regarding our model. This means how many concepts of our model this assessment handles. And you can see it goes from 5% to up to nearly 60%. Another interesting and important analysis is to see the status of validity and reliability of those assessments. The reliability was only reported for 3 assessments. All have used Cronbach's alpha. And the validity was reported for 5 assessments. Here different methods were used. In our eye, the assessment by Porter et al. Was evaluated in terms of reliability and validity the best. So if you're looking to do these kinds of analysis, we would recommend to take a look at their paper and maybe following the steps. Because the original paper where the assessment was introduced does not necessarily have to include these kinds of analysis, we also took a look at papers who cited the original one. So maybe a follow-up paper was published which showed a rigorous reliability analysis, for example. Here you can see the citations divided in a replication paper, which strengthens the claim of validity and reliability, a use paper, which are paper which have used the assessment in another context, for example, but have not reported the results in such a way that we could make claims about validity and reliability, and mentions papers. These are just papers which said, yeah, so these researchers have published an assessment, for example. So, but now we come to the question, what does this all mean for us and our goal? Well, first of all, I would encourage all researchers who publish assessments to also include analysis about the reliability and the validity of an assessment. Okay, so should we throw out the assessments which did not report on validity and reliability? And I would say no, of course not. We think that these are great assessments, and in most cases they were used in real case scenarios. Therefore we think that they might be valid and reliable. So we think that these assessments should be used, but when you use them, please report on the validity and reliability in your context. And this would help us and other researchers as well to build a database of reliable and valid assessments. So let's come back to our goal. A lecturer should be able to define which parts of our model of programming are relevant to him or her. And a suitable assessment should be available for him or her. Therefore, we think that more specialized assessments are needed. For example, like the one by Ed Hardy and Lister, which focuses just on variables. We also think that the validity and reliability of assessments would be much better or easier to assess when the focus of assessment would be more narrow. Now you can think, okay, an assessment of variables, I have a few thousand other topics in my course as well. So let me explain what I have in mind and what I would like to see if I could wish for anything. So imagine each of these narrow assessments, like the one for variables, are validated and reliable. So you can be sure that someone really gets variables when no errors were made when taking this assessment. Let's call them micro-assessments. And imagine for each part of our model such a micro-assessment exists. Now you could combine and pick the parts of the model which are relevant to you, and an assessment could be constructed out of many micro-assessments. And this constructed assessment would be the perfect one for your course. So you could possibly have an infinite amount of assessments if you would have such a pool of micro-assessments and could build an assessment for any context. Of course, I know this requires a huge amount of work and many empirical studies. But the end goal seems so beautiful that I am very passionate about it, and hopefully I got your interest too. So I'm very curious of what you think about micro-assessments and would like to discuss the future of programming assessments with you. And at the end of my talk, I want to say thank you for all the great assessments researchers have created, and I hope that I can do my part as well. Thank you very much.